Okay, now we're going to talk about surface integrals. And in this case, in this section, we're changing f, the surface that represents s, we're changing it to g instead, okay? So if you have your if you have your surface, say that this represents your surface s, then it's going to be in this section represented by z equals g of xy, for reasons which will soon become apparent. Let's talk about the surface integral of f over s. So what are we going to do? We're going to take, if you think about what the formula was for the area of a surface, in the last section, it was, remember, the double integral over s ds. Notice I put a space in there between the integral symbols and the ds, because guess what we're going to do? So this was the formula for the area of a surface. Remember what ds stood for. Ds stood for the square root of 1 plus, okay, in the last section it was f sub x squared, f sub y squared. But here, instead of using f, we're representing the surface s by g, so it'll be g sub x squared plus g sub y squared. So if this is all we wrote, this would be the surface area formula, right? But we're going to stick a function in here and create a surface integral. And the function is going to be called f. That's why we switched letters here. So the function is going to be called f of x, y, z. What could f of x, y, z represent? Well, I mean, it could represent like a density function in mass per unit area. And so when you integrate, just like when you find the mass of a planar lamina, when you integrate just the density function, remember you're finding what? You're finding the mass of that entire lamina. When you integrate over rho, which is the density function, you find that gives you the mass of the lamina. Remember that? Here the lamina isn't flat. Here the lamina is some surface. But if f of x, y, z represents the density function of that lamina, then, which I don't know if lamina would be the appropriate name anymore, because lamina probably means flat surface, but for the sake of argument, call it a lamina, then it would still represent, if you integrate that density function, it would still represent the mass. But the real reason we're going to define this is for later on when we talk about a flux integral. So that'll be the main application, actually. So this is a surface integral of f, some function f, over s. If this f that we're sticking in here is just 1, then what are we finding? We're finding, so this guy's just 1, we're finding surface area, right? Yeah. Then the integral, I'll just say it in words. Then the integral gives surface area. Of s on the domain, whatever that is. Let's look at this example. Evaluate, so how would I read this? This is a double integral over s. It's a surface integral, double integral over s of x minus 2y plus z ds, where z is equal to the plane 15 minus 2x plus 3y. And thankfully, you're told what the restrictions on x are and y. There's nothing to figure out here. So x runs from, as far as limits of integration, that is, x runs from 0 to 2, and y runs from 0 to 4. So I'm not, you don't want to take the time to graph these things, the surface S every time. But basically, this formula, how do I know it's a plane? Z equals 15 minus 2x plus 3y? It's a linear equation in space, right? If it's a linear equation in space, it graphs to be a plane. In other words, if all the exponents on x, y, and z are 1, it's a linear equation. And we know linear equations in space graph to be planes. So It's just a portion of the plane. It's the portion of the plane you would get if you restrict x to lie between 0 and 2 and y to lie between 0 and 4. Do we have to graph it? No. Just no, that's what we're integrating over. So the points on that plane, that's what we're allowed to plug in for x and y, and then ultimately you get z based on those points as well. So our g of x, y then, z, that plane, this guy, is g of x, y. Z is g of x, y. All right, so let's write down the formula and just analyze what it's telling us. Remember, the generic formula is the integral over s, f of x, y, z, ds. So if you use the calculation formula, just remember it's the integral over r, it's going to become, of f of x, y, okay, z is really g of x, y, at least on the surface, right? And then ds is the square root of 1 plus partial with respect to x squared, partial of g with respect to x squared, partial of g with respect to y squared, and then dA. So you got to have that formula at your fingertips. And it really just comes down to knowing what ds is, right? And by the way, that's a helpful way to remember all these formulas in this chapter. What does the differential represent? D capital S versus d lowercase s, right? D lowercase s is an infinitesimally small piece of arc length, whereas d uppercase S is an infinitesimally small patch of area on the surface S, right? So, and know the formulas for those things. That's really important. And then you can set up the integrals based on, or at least in part on that. So what is this lovely, beautiful formula telling you? No, some people say it's ugly. It's not. It's beautiful. What does it tell you need to find? It's whispering to you. Look at the inside. So if you're thinking this is an ugly formula, you should look at the inside of it, right? Right? It's what's on the inside that counts. And the inside tells you what you need to find, right? So the partials, yeah. If you look, okay, you look inside the integral symbols, and then you look inside the radical notation, and you see it, and inside the squaring functions, and you see g sub x and g sub y, don't you? So we're going to find the derivative of g with respect to x. That's the same as z sub x, right? So what would that be? Negative 2. Oh, that wasn't that bad. G sub y. 3. And then what would be then the area element? The square root of, we take 1 plus g sub x squared, what's that? 4 plus g sub y squared, 9, and then ultimately that'll be root 14, won't it? Okay, I think we're ready to set this thing up now. So this integral then, in terms of this problem, it'll be the double integral over r. Oh, well, if we go with the dy dx order of integration, then what would the inner limits of integration be? 0 to 4. That would be on the y, right? And then for the x, 0 to 2. Okay, if you think of f as this guy, you're golden. Except you have to remember to do what? Yeah, you can't have 3 variables in a double integral. Doesn't work. So you know what z though is on the surface, and that's all that matters because you're integrating over that surface. So you can replace z with this formula right here. Does that make sense? Okay, so I'm gonna write what it is in terms of z, and then I'll fix it. So the f then is the thing you're given here, and then that's x minus 2y plus z. I'll fix the z in a minute, and then square root of 14. That's this part, and then dy dx is your dA. So that's initially the setup. Does that make sense? And it doesn't really matter when you plug. I could have plugged in for z already. It doesn't, as long as you do it, eventually it doesn't really matter when. Okay? So if at this point you didn't realize, oh yeah, I can't integrate this because I can't have z in there when I have just differentials dy dx, a double integral. So now, if you haven't done it already, replace z with what it's equal to, x minus 2y plus z. Oh, okay, z is, so I'll put brackets out here and then parentheses around the z that I'm plugging in. So 15 minus 2x plus 3y, that's my z, and then I close the bracket, and then I still have the square root 14, which I suppose I could bring out front of the integral. And then dy dx. Does everybody believe that? Okay. So let me go ahead and bring that root 14 out. And then integral 0 to 2, integral 0 to 4. All right, let's combine like terms. How many x's do you see?
2.
I see, well, yeah, okay, I see two different terms with x's, but what about when you combine them? What do you get? Negative x, sure, negative x. And then the y's, so plus y, and then we have a 15 still, right? Didn't miss anything, I don't think. The root 14's out front, dy dx. So we integrate this, okay, square root of 14, integral 0 to 2. Okay, integrate this for me. With respect to y, what do we get? Okay, so negative x times y, y squared over 2 plus 15y dx. Oh, what are we evaluating that from? Whoops, that should be a dx on the outside. 0 to 4, right? Okay, and then we get the square root of 14, integral 0 to 2. Okay, we're plugging in for y equals 4 and y equals 0, right? So what do we get when y equals 4? We get, yeah, let's write it as negative 4x. Let's see, 16 divided by 2. Plus 60, and then the 0 zeroes everything out, doesn't it? Everybody with me? All right. And then integrate. Try to inflect my voice and make it exciting, even though it's not really that exciting. Okay, integrate negative 4x. What do you get? Yeah? Plus 68x. Whoops, not there, but there. Everybody with us? Okay. And then we're integrating that from, you know what, I like evaluation brackets. And then integrate from, okay, 0 to 2. Okay, so what does all that mess turn out to be? So negative 8 plus 1, 36? I believe that. So 128 root 14 would be a good way to write it? Yeah. There we go. We need to talk about surface orientation. We're going to be talking right now about a normal vector n, okay, to a surface. In fact, we're going to make it a unit normal vector. I can think of two ways to orient this thing in terms of a unit normal vector or just a normal vector. I can think of a normal vector that points kind of upward here, the one in green. But wouldn't the vector that points inside the surface kind of, or down, generally downwards, wouldn't that also be a normal vector? So I guess my point is, isn't there two normal vectors for any surface? So two ways to orient a surface using a normal vector n. For the upward n, the k component's positive, downward n, k component negative. How do we orient a surface? We orient a surface by choosing. I gotta fix that. By choosing an orientation for n, and you stick with it. Okay, you don't want n at one point being upward pointing and at another close by point being downward pointing. Okay, you don't know why yet, but just believe me, that's important. Now, a couple of notes here. A closed surface is a surface like a sphere. Okay, it describes a region in space inside the sphere, and it closes off the outside. It closes off the region inside the sphere to the region outside the sphere. So we call it a closed surface, like a sphere is a closed surface, an ellipsoid is a closed surface. And there's lots of others. For a closed surface, S, n always points outward. That's by convention. For a closed surface, you always orient your surface by choosing the outward pointing normal vector. Number 2, n must vary continuously for S to be orientable. In other words, if you want to orient a surface using a normal vector, you can't have n pointing upward or outward or inward at one point, and then all of a sudden at a nearby point have n pointing in the opposite direction all of a sudden. It has to change continuously. And then, in case you need it in vector calculus, if S is defined by R of uv, a vector valued function, then you actually use n, your normal vector, to be Ru cross Rv divided by its magnitude. But again, in this class, we won't be needing this formula. But you might take vector calculus, and then at whatever school you go to next, and that formula will come up, and you change the surface integral appropriately. Okay, so all of that's kind of mysterious right now. Why do we want to orient a surface with a normal vector, right? Let me show you. Flux, a flux integral. A flux integral measures the quantity of fluid passing through a surface per unit of time. Okay? The surface can be imaginary. It doesn't have to be real. It can be real, it doesn't have to be. The fluid can be a gas. It can be an actual liquid. And we also can use fields like magnetic fields and electric fields, and we think of them as, they're not really fluids, but we think of them as fluids. And we use surface flux integrals by analogy to analyze electric and magnetic fields. So let me show you what I mean by finding the flux that passes through just a little small patch of our surface. So this in red, imagine, is some surface in space. And let's break it up into a grid of rectangles, or almost rectangles. They're closer to parallelograms, but they're not even parallelograms. Okay. So let's suppose we break it up like so. And let's analyze one little patch, maybe this patch right here. I'm going to blow it up in a second, so that's okay. So imagine analyzing that patch. Now, you have to imagine that this surface is immersed in some vector field. So you've got vectors from F all around it. All around it. And let's put one of the vectors from F at, say, a corner. Oops, I shouldn't have done that in blue. Let me highlight it in green here. And let's put one of these vector F's at a corner here. And of course I should have made that blue. Okay. Then check this out. For a really small patch of surface, F is going to be nearly constant flowing through this patch of surface. And if I draw a good picture here, I'm going to have to zoom in to make this look decent. Yeah. Okay. So here's F at this corner of my little, it's almost a parallel, this patch is almost a parallelogram. Here's a vector from the vector field F at this corner, and at the back corner. What is this starting to look like? This, if I attach the vectors with edges, you can imagine, let me erase. Let me erase, this guy's gonna get in our way here. So remember, F is a velocity field of some fluid flowing, okay? And all of these vectors are edges. All of these edges on this figure, this solid I've drawn, represent vectors F. What does this start to look like? So think of this as a snapshot of the fluid flowing through a patch on your surface in 1 unit of time. What does this start to resemble? We actually have a name for it. It looks like if all the sides are parallelograms, it's called a parallelepiped. Now they're not quite parallelograms because this patch is not quite a parallelogram, but it's close enough. Okay? So the idea is if I could find the volume of this almost parallelepiped, then that's going to be the flux through the surface, through this little small patch right here. And then the idea is if I can add all of those volumes together through all these infinitesimally small patches, then I'll have my way to measure flux through the entire surface. And that is going to be represented, as you might imagine, by an integral. Okay, so let me derive this formula for you. So let me expand on this idea of a parallelepiped. So what's the volume? So the flux through this little patch of surface, the patch being this guy in green right here, the flux through the patch of surface is going to be given by the volume of the parallelepiped. I'll put that in quotes because it's not really quite a parallelepiped, but as you make this grid of surface patches finer and finer, it gets closer and closer to a parallelepiped. So let me move this over. And so we're referring to this parallelepiped right here. Okay, so does that make sense, by the way? This would be a good time to ask questions if you got it. Okay, so we're just trying to find the volume of this parallelepiped, and that's going to be a good, it's an approximation of the flux through that patch of surface. Okay, so yeah, it really is approximate. So what's the volume of a parallelepiped? Well, you're going to take the height of the parallelepiped, the vertical height, so like measuring from like here to here would be the vertical height, right? So you're going to take the height times the area of the base. The area of the base is easy. The area of the base is ds, right? That's what ds represents. The height, that's what we need n for. Okay, let me erase this representation of height and show you how we use n to get the height. So n in my little picture here, we'll do n in pink, I guess. N in my little picture here might look like this. It's got to be normal to the surface, right? So so translating that n over here, there, right? And if we look at the angle formed between n and one of the vectors from F, we could call that theta. We could use a projection here, but we're not. We're just going to use a formula from trigonometry and form this right triangle right here. And realize that this edge of the parallelepiped is the magnitude of this vector from the vector field F. And then we can get the height by using simple trigonometry. What would the height be? It would be the magnitude of F times, well, this angle is the adjacent angle, right? So cosine theta. And then the area of the base is ds. Okay, now we're almost there. stick with me. I'm going to stick in the magnitude of n. The magnitude of n is just what? Is it okay just to throw in a magnitude of n? N is a unit vector, right? So I'm multiplying by 1. Why did I do that? What does that do for me? Well, there's another name for the magnitude of f times the magnitude of n times the cosine of theta. It's the dot product of f and n. And so what we get for, we'll call it a flux element. Our flux element is f dot n ds. And we're going to use this to create a flux integral. So let's call this a flux element. And we've essentially got it. Now imagine summing all such flux elements together over that grid of patches, and then taking the limit as that grid gets finer and finer. And if that's a Riemann sum, and if that limit exists, you've got yourself a flux integral. Okay. So let's fill in the box then. Based on that flux element, what should the flux integral look like? Well, it is a surface integral. Double integral over S. The flux element is what we're putting in that integral. F dot n ds. Now the actual calculation formula that we use for the flux integral. So by the way, whenever you see this, you think flux integral, okay? Flux. The flux integral, f dot n ds, calculation-wise, we're going to use this formula. We can use little g to come up with big G. And then depending on how we want to orient it, we'll take plus or minus, we'll take f dot plus or minus del G dA. Now, why? I mean, your question should be, why is this flux integral equal to this? Why? Well, okay, if you go back up and look at del G and look at what ds is, you'll see that if you express n as del G divided by its magnitude, right? N has to be a normal vector. If you look at the ds part of it, then you remember what that was in terms of the square root dA? It was 1 plus g sub x squared plus g sub y squared. But that's exactly what the magnitude of del G turns out to be, okay? So that's where this calculation formula, these guys cancel, and that's where this calculation formula comes from. Consider f of x, y. So your vector field is given by components x plus y, and z. S is the closed surface given by z equals 1 minus x squared minus y squared, and z equals 0. And you're asked to find the flux integral, f dot n ds. So the first thing to recognize is that you're dealing with a closed surface. Can you guys tell me what this surface looks like? What kind of surface is that? It's actually a paraboloid, isn't it? That opens down. The vertex would be at 0, 0, 1. And it is not a closed surface, is it? I could do better than that. So it's not so this would be the paraboloid represented by z equals 1 minus x squared minus y squared. This is not a closed surface. To make it closed, we cap it off on the bottom by by the part of the xy plane, z equals 0, that's underneath the paraboloid when it intersects the xy plane. So it's capped off down here. But this is just inside the disk created by the intersection of the xy plane and the paraboloid. That flat disk is just part of the plane z equals 0, part of the xy plane. So taken together, the paraboloid, which we'll call S1, and the disk that you get when you intersect the paraboloid, so when z equals 0, you get a disk, 1 minus x squared minus y squared, which is the same as x squared plus y squared equals 1, or less than or equal to if we're talking about the disk. It's capped off. To make it a closed surface, we cap off the paraboloid with this disk. Okay? And that z equals 0 is what we're going to call S2. Okay? So S, this thing that we're integrating over, is actually the union of two surfaces, S1 and S2. And it is going to turn out that when you integrate over the union of two disjoint surfaces, you can integrate individually over both surfaces and sum the results. Okay, so what do we do? So let's calculate the integral over S1 of f dot n ds. Okay, get in the habit of writing down your calculation formula. Your calculation formula tells you what you need to find. So how do we parameterize a closed surface by convention? Or orient, I said parameterize by mistake, I meant orient. How do we orient a closed surface by convention? We take the outward pointing normal vector. Okay, so this vector is normal with the surface, and so this is the outward pointing normal vector by convention. And in the calculation formula, we take f dot, okay, del g, it's got to be positive del g because that has the k component of any vector on the paraboloid is going to be positive. You can tell, just draw a few of them. It might get almost flat, but it won't get totally flat until you get on the edge here, which won't matter. Okay, so we're going to take the calculation formula to be integral over S1 f dot del g dA. Okay. All right. So we need to figure out what del g is. In order to do that, we have to figure out what g of x, y, z is. Okay. Okay, go back up here. For the paraboloid, this is lowercase g. The paraboloid is lowercase g. How do we come up with uppercase g? Uppercase g is what you get when you set this equation equal to 0, okay? And leave the thing with z in it positive. So that means get the 1, the minus x squared, the minus y squared over to the other side. So we get x squared plus y squared plus z minus 1. X squared, whoops, x squared plus y squared plus z minus 1. Whoops. Okay, that's the capital G from del G right here. Now, del G will be normal to S. Okay? Del G will be normal to S. So, because del G is normal to the level surfaces, that is, of S, which little g is. Okay, so del G, you're just computing a gradient here. which means you take the partials with respect to x times I, partial with respect to y times j, partial with respect to z times k, where the function you're taking the partials of is capital G. So del G is 2xi plus 2yj plus k. All right? And then you want to look, now let the formula guide you. You want to take f, the vector field f dot del G. Okay, so if we do that, f dot del G. Okay, let me remind you what f is, because it's way up here. F, let me grab a hold of it, a copy of f. And let me put it down here. And then we can take the dot product. So this guy is our f that we're given. This guy is the del G that we had to come up with based on lowercase the function lowercase g that gives s. And now we want to take f dot del G. So what is that going to be? Well, it's just a dot product, you guys. So 2x squared plus 2xy when we take the first components and multiply them together, right? See that? So I'm going to distribute the 2x and get 2x squared plus 2xy plus 2y squared plus z. Okay, but we're just going to end up with a double integral. We can't have z in it. So what is z? Z, we're doing everything on the surface, right? So z is g of xy. So you can replace any z with, since we're on the paraboloid, you can replace any z with 1 minus x squared minus y squared. So if you replace with 1 minus x squared minus y squared and add like terms, you'll have your integrand. So, okay, we have 2x squared minus x squared. What's that? So I'm going to put this guy in for z, in other words, and if I add like terms, I get 2x squared minus x squared. That's just an x squared left, right? And then if I take the 2y squared and minus y squared, I'll put the y squared right there. And then the 2xy is fine as is. So that's my integrand. Okay? A little complicated, I know. So then the flux this is just symbolism here. The flux integral over S1 then, which we can represent like that, can be calculated using, okay, R is going to represent what you get when you project S1 into the xy plane. R, and then the integrand is this guy, x squared plus y squared plus 2xy, and then dA. Okay?
There's supposed to be a 1, it's all supposed to be adding by 1, or there's supposed to be a 1 at the end.
Did I forget the 1?
Yeah.
I did, you're right. Sorry about that. I did that just to see if you're paying attention. Okay. So, do you guys see what he's talking about? We needed that in there, right?
Yeah.
So plus 1. I was trying to save time, and then, of course, when you do stuff like that, you end up missing something. Okay. So now does it make sense to you? Okay. Now, look. When we project down, when we project this paraboloid down in the xy plane, like I've already said, you get the disk, right? So that R ends up being the disk, x squared plus y squared is less than or equal to 1. So how are you going to integrate this? Good old polar coordinates. So it's going to be the integral, just like earlier. R is going to go from 0 to 1, theta from 0 to 2 pi. Okay, now do this in an easy way. Don't individually substitute r cosine theta, r sine theta. What is x squared plus y squared? R squared. So that's the best way to substitute. r squared, whoops, and then plus 2xy. Okay, x is r cosine theta, y is r sine theta, so you're going to have an r squared there, right? And then cosine theta, sine theta. And then you do have that plus 1 there. Okay, what is the area element when you switch to polar? RD theta. And so this is the last part of it that I'll do for you. You're going to want to distribute that r, and you'll get r cubed plus this r right here, right? Plus r cubed cosine theta sine theta plus another r, right? And then d theta. If you evaluate that integral, again, I'm just going to give you what that turns out to be. Let's see, there's a 2 somewhere that I'm missing. Right here, right? 2? Yeah. Okay. If you evaluate that integral, that turns out to be 3 pi over 2. Okay? Now, you might think there's no way we could integrate over S2 in the 1 minute we have, well, in the no minutes we have remaining. But you'd be wrong, because it's 0. Look. The orientation vector, the normal vector we use to orient this z equals 0, that's what S2 is given by, z equals 0, is straight down. It's a unit vector pointing straight down. It's negative k. So what do we get then when we take f and dot it with negative k? I don't need to use the del G formula here. Look, guys, if you actually take this dot product, k is the vector 0, 0, 1, negative 1, negative k is the vector 0, 0, negative 1, right? What's the k component of f? The k component of f is z. Everything else zeroes out when you take that dot product. So this just becomes the integral over S2 of, okay, negative z. But z is equal to 0. So you're integrating 0, which is 0. So the integral over S, which is the integral over S1 union S2 f dot n ds, this flux integral would be the sum of the integral over S1 plus the integral over S2 and plus, I was thinking plus ahead of time, that's a dot product there, f dot n ds, but we know this one's 0, and we know this one, I think it was 3 pi over 2. So you add them, and last time I looked, 3 pi over 2 plus 0 is just 3 pi over 2. Okay.